Hello everyone, welcome back to another video. In today's video we are going to be taking a look at a cup filled with water up to a certain level, and what is going to be happening to this cup is it is going to be sitting on a turntable which is going to be spinning that cup in circles round and round, and what is going to be happening to that water is going to be accelerating towards the outside rim of the cup, causing it to the fluid level to rise as you get closer to the edge of the cup and sink the closer you get to the center of the cup, right? And what we're going to be trying to solve is we are going to be trying to figure out what the maximum angular acceleration is that we can rotate this cup before that water rises to a level that will cause it to spill out of the cup, right? So pretty much the height of this cup is going to be the limiting factor of this, right? We can spin this as fast as we want to up until the point where this fluid level is going to become so high that it gets higher than the rim of the cup, and eventually starts to spill out, right? And pretty much how we're going to be getting into this is we are going to be starting out with our basic equation of static fluids, which we've been using in the previous few videos, which pretty much just says that the differential change in pressure over a differential change in position is going to be equal to the density of the fluid within the cup multiplied by the acceleration, right? And the acceleration that is going to be happening in this situation is a centripetal acceleration, right? All right, it's also important to consider the direction of this acceleration right here. So obviously, this cup is going to be accelerated inwards. So we'll just go ahead and draw this up. So say this is the bird's eye view of the cup looking down on it, right? And this cup right here, this cup is going to be getting accelerated inwards. So it's not flying off the turntable. So this is going to be keeping the cup steady sitting on the turntable, but the fluid inside it is actually going to be getting accelerated outwards, right? This is what is causing it to want to move towards the outside of the cup, right? So that is going to be the direction of our acceleration. And this acceleration, it is going to be a centripetal acceleration, right? So the equation for centripetal acceleration is equal to r, which is going to be the radius of this cup right here, right? So we'll go ahead and drop our r variable. Just going to be the halfway point all the way out to the edge of the cup. That is going to be our variable r. That is the radius of this cup. And then this is also going to be multiplied by w squared right here. W is just the angular acceleration of the cup on the turntable, right? This is what we're going to be trying to solve for later. What is the maximum angular acceleration we can get on this cup before the liquid will spill outside the edge of the cup, right? And basically we can go ahead and substitute this in for our A over here. And we'll go ahead and multiply dz over to the other side. So this, once again, is the density of the fluid within the cup. And this dz is going to become a dr, right? This just means the differential change in pressure over the differential change in some sort of position. This position, in this case, is going to be based on the radius of the cup, so that's going to become a dr right there. And pretty much what we can do now is we can go ahead and integrate, right? This density is going to be constant, and this angular acceleration is going to be constant, so we can pull those out of the integral. So this is going to become the integral of dp is going to be equal to density of the fluid times the angular acceleration squared, r dr. And it is also important that we include our parameters of the integration, where we're starting and ending our integration from. And this is pretty much just going to be from the first radius to our final radius right there. And this is going to be from our first pressure to our last pressure. like so. And we'll go ahead and figure out this integration right now. This is going to be P minus P1 is going to be equal to rho W squared, right? And then this is going to be just a really simple integration, right? This is going to be 1/2 R minus R1 squared. So we'll go ahead and do that. All right, and as you can see here, our R1 is going to be the very center of the cup right here, and our second R is going to be some position that we choose outward right here. So this R1 is going to be 0 because we're starting at the center of the cup, which means that the radius is going to be 0. So that'll go away right there. And then this P1, as we can see here, this is going to be at radius 1. And at radius 1, there's going to be no fluid above where the position is, which means there's going to be 0 pressure, right? If you have no fluid above the position, that means that there's going to be no pressure on it because there's no pressure on it from the air. You need fluid above it for there to be pressure, and since there's no fluid, there's going to be no pressure there. So we know that P1 is also going to be 0, right? And pretty much what we can do now is we can say that P is equal to rho W squared R squared over 2, like so. And we know that our pressure here is going to be equal to rho GH, right? So pressure is equal to rho GH. This is saying that pressure is equal to the density of the fluid times the acceleration due to gravity times the height of the fluid above it. This is why we said the pressure at R1 is going to be 0 because there is no height of the fluid above it. We are taking the pressure kind of along this line right here. And as you go outwards towards the brim of the cup, that pressure is going to go up because there's going to be a higher fluid. But at the center position, it's going to be 0 because there is no fluid right here. So we can go ahead and substitute our rho GH in for P over here. So we'll go rho GH is equal to W squared R squared over 2. Can't forget our density of the fluid on this side. There we go. As you can see, the density of the fluids are going to cancel. And then to get our equation for the height of the fluid, we just have to divide both sides by the acceleration due to gravity. So H is going to be equal to acceleration due to gravity, or angular acceleration, excuse me, this is the angular acceleration squared, times the radius of the cup squared over acceleration due to gravity times 2. Probably be simpler if we wrote 2g instead of g2. So we'll go 2g. There you go. This is going to be our equation for our h variable over here, the height of the liquid. Alright, so before we go further along in our video, I first wanted to explain what this h variable is. I feel like I didn't do a very good job of explaining this. So pretty much all this is this is going to be a height, a certain radius away from the center of our cup, right? So we have this expression right here. This initial R1 is going to be the center of the cup, and then we move away a certain radius away from the center. So we'll just say we are going this far out, right? And then this height is going to be right here, is going to be this position right here. So this is going to be the change from the center of the cup to the position at that radius, right? So say we want to go a little bit further out, we pick a radius that's a little bit larger. We go, say, let's go this far out. This is going to give us this height value right here. Say we want to go a little bit shorter, we pick a radius that's a little bit smaller. This height is going to be this right here. So this is going to give us the change in position from this radius we pick all the way from the center of our cup right here, right? That is going to be what this h expression is giving us, right? And the next thing we are going to want to do is we are going to come up with an expression that comes up with this d value, right? This is going to be the depression of the height at the center of the cup. This is going to be the change in the height from where it was over here when the angular acceleration was 0 and the cup was just remaining steady. This is going to be how far down the depression in the water level is at the center of the cup, right? And we're going to go ahead and hop into that now, and we're going to be coming up with an expression to relate this depression value to the radius of the cup and the angular acceleration. Alright, so in order to find the value of this depression right here, we are going to be doing some calculations for the volume. And before we get into that, I think it's important to take a look about how the volume is changing from when the cup is steady and not moving and has this flat surface versus when it is being angularly accelerated and creating this sort of parabola right here. So firstly, we know that the volume of this area right here and this volume right here, where it starts at the lowest point and goes all the way across, these are going to be equal to each other. And we know that no fluid is being added or taken away when we start to accelerate it, right? Because we are keeping all of the fluid within the cup. We are going all the way up until the point where the fluid reaches the brim of the cup, but none of it is going to spill over, right? So that means since this value right here and this value are equal, that means that the volumes over here in our side pieces right here and our area above the lowest line of the depression, those are going to be equal, right? So we'll go ahead and erase this right here so it's easier to look at. So the volume in this point where it reaches the lowest depression point and its starting fluid level is going to be equal to this point over here where it is at the lowest depression all the way up to the brim of the fluids, right? Obviously, we know that the volume of this over here would be easy to calculate. You would just do the area of the circle, pi r squared, times the height of it over here. But it's going to be a little bit more complicated calculating the volume over here, where it starts to create that sort of cone shape, or not cone shape, but a parabola shape. And so in order to do this, we're going to again take a look at the eagle eye view of this cup over here. And we are going to be just taking, we're going to calculate the volume at certain radiuses, and we're just going to keep going out until we add up all of the radiuses or the volumes at a differential radius, and we're going to integrate that to add them all up, and that is going to give us the volume over here, right? So this is going to be some dr. We're going to calculate the volume at that dr, and then we're going to add up all the differential volumes, and that is going to give us the regular volume, right? So we know that the volume for this over here is just going to be pi r squared times d. D is going to be the depth that of the lowest point that it reaches, so we'll go ahead and write that out. We'll write that right here. And this is going to be big R, right? This should be right here. This is big R. This is the full radius of the cup. This is not being split up into a partial radius. This is the full radius, the maximum radius you can get. And we know that the differential area at a certain radius is pretty much just going to be equal to the circumference at that level times the differential radius, right? So dA is going to be equal to the circumference times a differential radius like we have here. And we know that the area of the circle is just going to be 2 pi r, so this is just going to be dA equals 2 pi r dr. And then to turn this into a differential volume, all we have to do is multiply it by the height at that differential radius, right? That is going to give us that third dimension, turning the area into a volume. So the differential volume is just going to become 2 pi h r dr, like so. And now all we really have to do is do some integrals right here. And the bounds of integration for this are going to be from 0 to big R, right? Because we are starting at this point where the radius is 0, and then we're going to add up all these differential radiuses all the way out to the edge of the cup. And remember, we said the edge of the cup has a radius of big R. That's the maximum radius you can reach right there. So the bounds of our integration are going to be 0 to R, right? Alright, so now that we have our integrals set up and the bounds of integration set up, we can go ahead and solve for this. And since we know that the integral of this differential volume right here is just going to be the regular volume, we know that it's just going to be pi big R squared times d. This is going to be the left side of our equation right here. So we'll just go ahead and start writing this up right here. So we're going to have pi r squared times d. This is going to be our regular volume right here. And then we know that this 2 pi, that's just a constant. That's just not going to be involved in the integral at all. So we'll go ahead and write that up outside. And we already have our equation for this height right here. We can use this expression right here to represent h, so we can go ahead and substitute that in. And this w squared 2g, that would not be involved in the integral. That is all constants right there, so that can be brought out. So we're going to have a w squared over 2g. But then we do also have this r squared that we would have getting multiplied by this r. So that is going to be involved in the integral. This is going to turn that r into an r cubed, right? We have an r times an r squared turning it into an r cubed. So this is going to be the integral from 0 to big R of r cubed dr right here. Before we set up this integral, we can see that we have a pi on both sides. Those are going to cancel. And then we have a 2 right here, and then we have a 1/2 right here. Those are going to cancel out like so. Go ahead and erase this down here. Alright, so right now we have big R squared times d is equal to our angular acceleration squared over the acceleration due to gravity multiplied by our integral from 0 to big R of our little r cubed dr. Now this is a pretty simple integral to do right here, right? This is just going to turn into, well, first of all, we know that at 0, this is just going to become 0, right? At 0, at our position 0, we have no radius, so we're not going to have to worry about our lower bound of integration. We're just going to have this r. This is going to turn into a 1/4 little r to the 4th, and pretty much you just substitute the big R in for the little r. That is going to turn into a 1/4 big R to the 4th. So we can go ahead and erase, or not erase this, we'll go ahead and just do the next step down here. Big R squared d is equal to w squared over g, and then this would turn into big R to the 4th, and then that would also have a 1/4 attached to it. As you can see, we have an r to the 4th over here and an r squared over here. Those are going to cancel. That's going to become a squared over here. And then we're left with just d over here, which is our depression value again. This is what we're trying to solve for. So pretty much we have this expression done. We just got to rewrite it over here. Our depression is going to be equal to, let's see here, w squared big R squared all over 4g. And there you have it. That is going to be the value of our depression from our starting fluid level based on a certain angular acceleration and based on a certain radius of the cup we have. And yeah, that is just going to be the two values. These are going to be two big equations. Let me go ahead and erase this. These two equations that we have written up on the board, these two right here, these are going to be the big equations that we are going to use to solve for the maximum angular acceleration we can have before the fluid overflows. And we'll go ahead and get into solve for the maximum acceleration now. Alright, so now we are going to go ahead and get into solving for what that maximum angular acceleration is going to be before we do reach the tipping point where the fluid is going to start flowing over the brim of the cup. And this is going to be surprisingly easy. We've already done all the homework trying to get our depression right here and our height at a certain radius away from the center of the cup. And yeah, pretty much all we're going to be doing is, first of all, we're going to break up this big H right here. This big H is the total height of the cup, and we know that we can get this height all the way up until the depression by subtracting the initial height of our fluid when it is just steady with no angular acceleration going on, when it's just flat and steady. That is going to be our HO, and we can subtract that from the depth to give us this volume right here below the depression, right? So this big H is going to be equal to our HO minus our depth. That is going to give us this height right here. And then to get the rest of this, right from here to here, all we have to do is we have to find our height at our maximum radius of the cup, right? So earlier we were saying, we would pick this radius right here, and when we plug that radius into this equation, it would give us a height up to here. But if we plug in the max radius of the cup all the way out here, that height would give us this right here. And if we add up this and this, that is going to give us the total height of the cup, right? So we can just say plus our H of R, right, to represent that we are plugging in the max radius of the cup, all right? And pretty much we've already done most of this. We've already have these equations written out. So we'll go ahead and subtract over our HO right here. We'll have H minus HO. That is going to be equal to D, which we'll go ahead and plug this equation right here in for D. We'll have angular acceleration squared times radius of the cup squared over 4g. And this is going to be a negative. Can't forget about our signs. Negative. And we'll have HR. And since we are doing this at the maximum radius of the cup, as far as you can go, this little r is going to turn into a big R squared, right? So this will be plus angular acceleration squared over big R squared all over 2g. And this is looking good right here. As we can see, we have our w squared r squared over g, and all that's really changing is our sign and the number we have in the denominator right here. So pretty much we can think of this as 1/2 minus 1/4, right? And what that's going to turn into is a positive 1/4. So we can go ahead and say that this is the height of the cup minus the initial height of the fluid with no angular acceleration. Then this is going to be positive 1/4 w squared r squared over g all over 4. And yep, we are pretty much looking to solve for this angular acceleration. So we'll just go ahead and move some of our variables around, do some algebra right quick. All right, just realized we forgot to include our acceleration due to gravity over here in the denominator right here. That's important. Make sure you guys don't forget that. And from here, all we really have to do is do some simple algebra. So we'll go ahead and multiply that 4g over and then divide by r squared because we want to get our angular acceleration by itself. That is the variable that we are trying to solve for. So this is going to turn into w squared equals 4g h minus ho. And then we divide both sides by the radius of the cup squared to get that. And then all we have left to do is to square root both sides to get just a regular angular acceleration over here. So we're going to square root everything. This 4 would turn into a 2 that we could bring outside of the square root. And then the radius of the cup squared to the square root is just going to be the regular r. It's just going to turn into r by itself. No exponents on there, so this is going to turn into w is going to be equal to 2, and then we're going to have g h minus ho. That is going to be square rooted, and then that r squared just becomes a regular r, and there you have it. That is going to be our final expression. That is going to be the angular acceleration, the maximum angular acceleration you can put the cup under before fluid starts to overflow out of the top of the cup. And yeah, that is going to do it for today's video. I hope you guys found this interesting. Like the video if you enjoyed, and subscribe if you guys want to see more content. And make sure to have a good one.